So let's take a look at our final section, which is section 9.3, and we're going to continue our discussion about confidence intervals and hypothesis testing that we started in the last section, but now we're talking about, remember, the mean for a population. So just a quick refresher, confidence intervals, remember, are used to estimate a parameter. So estimate a population parameter. So in this case, we're going to use them to estimate the population mean. That's going to be our parameter based on some sample that we're working with. Hypothesis testing, remember, is an answer to a yes or no question. Hypothesis tests are used to decide whether a parameter's value has changed from some value we've had before. So we're looking at the mean for a population. So these are the same methods as introduced in previous chapters for population proportions, but this time we're modifying them to work with population means. So same concept, same logic. We're just going to use the t-distribution this time instead of the regular z-distribution. So for confidence intervals, remember that confidence intervals, they provide a range of plausible values for a population mean. It gives a measure of uncertainty in our estimate. So remember, the higher the level of confidence, the better our estimate is. So when do we use confidence intervals? We use the confidence intervals whenever we are estimating the value of a population parameter on the basis of some random sample. We do not use a confidence interval if there is no uncertainty in your estimate. In other words, if you know your entire population, there's no need to estimate a confidence interval. If you have data about every student at Flagler College and that's your population, there's no need to estimate using a confidence interval. So conditions to check for before we get into it, it has to be random and independent. Our sample size has to be large enough, it has to be at least 25, or they have to tell you that the population is normally distributed. And the population has to be big enough so that if the sample is collected without replacement, the population is at least 10 times our sample size. So let's take a look at an example. A used car website wanted to estimate the price of a 2012 Nissan Altima. The site gathered data on a random sample of 30 cars and found a sample mean of 16,610 and a sample standard deviation of 2736. The 95% confidence interval for the mean cost of this model car based on the data is given in the problem there. So part A says describe the population. Is 16,610 an example of a parameter or a statistic? So this first part really isn't anything new. We found a sample mean of 16,610. Of course, that's a measurement on our sample, so that would be a statistic. All right, so just review of the vocabulary. Remember, a statistic is a measurement on your sample. Part B says verify that the conditions for a valid confidence interval are met. Okay, so they told us that it was a random sample. So that was the first condition. The sample size is greater than 25 because it was 30, so we are good to go there. And then I think it's safe to assume that the population is large enough that there's more than 10 times 30 Nissan Altimas in the country. So the central limit theorem conditions are certainly met. A confidence interval provides a range of plausible values for the population parameter. Remember, we don't know what the population mean is, and that's the point of using the intervals to try to get an estimate for that. In the case of population means, we can be confident that if we were to someday learn the true value of the population, it would be within our range of values that are given in our confidence interval. So based on a random sample of 35 two-year colleges, a 90% confidence interval for the mean in-state tuition at two-year colleges for the year 2012-2013 is 2,611 to 3,227. When we examine the data for all two-year colleges in 2008-2009, we learned that the population mean was 2,517. So the question says, does the confidence interval that we came up with provide evidence that the mean tuition has changed since the academic year in 2008-2009? So this is just kind of a logic question. There's nothing to calculate here. What we're saying is that the confidence interval, so we had a 90% confidence interval for the 2012-2013 year that told us we think the population mean is between these two numbers. Okay. Well, in 2008-2009, we had a population mean of only 2517. So I would say yes, this gives us an idea. We're 90% confident that the mean was between 2611 and 3227. So I would say yes, since the confidence interval values are above, they're both above the mean that we had earlier in 2008-2009, which was 2517. So yes, I think this does provide evidence that the population mean has changed, and actually I think it's increased from the original academic year, but they asked us for has changed. All right, so how do we do the confidence interval? Let's talk about first how to do it by hand, and then we're going to look at what to do in StatCrunch. It's actually very similar or analogous to what we did back in Chapter 7. The difference is how we do some of the calculations. So remember earlier it was the estimator plus or minus the margin of error. The margin of error is going to be the multiplier times the standard error. And let me just back up. This is not for this. I just want you to remember back from Chapter 7, when we talked about confidence intervals with proportions, we said it was p hat plus or minus m. Just want you to have that formula in your mind. That's what we're saying here. The estimator, whatever we're using for our sample mean, plus or minus the margin of error is how we're going to get our confidence interval. It's the same structure. The difference is we're using a mean instead of a proportion, okay? So the margin of error that we're talking about is the multiplier times the standard error. And I'm going to show you the multiplier in a minute. The standard error is this formula right here, sigma divided by the square root of n. However, keep in mind, we probably don't actually know what sigma is. So instead, we're going to use an estimate for the standard error based on the standard error, or the standard deviation rather, from our sample size. And that's this formula I have circled below. So for a one sample t interval now, remember we're using a t distribution, which is a confidence interval for the population mean. Here's what we end up with. We end up with x bar, so my estimator plus the margin of error is x bar plus or minus m, and m becomes t star, and I'll show you what t star is in just a minute, times the estimated standard error, and we're going to use this formula where we use s, which is the standard error of our sample. The multiplier t star is a constant that we use to fine-tune the margin of error. It's just like the z star values we used earlier in Chapter 7. It's the same idea. This is found using a t distribution with n-1 degrees of freedom. And we'll do an example of all of this, so hang tight. I know there's a lot of information here. So, info needed to construct a one sample t interval. Our sample average, x bar, which you calculate from your sample data, the sampled standard deviation, s, which you also calculate from your sample data, the sample size, of course, is n, and the multiplier t star, which we're going to use StatCrunch to help us get that multiplier. We're not going to have to remember those or anything like that. The multiplier is based on your confidence level and your sample size, and it tells us how wide the margin of error needs to be in terms of standard errors, just like it was back in Chapter 7. So if I wanted a 95% confidence interval, I used a z-star value of 2. It's a similar idea, but it's just going to be different numbers. So let's take a look at an example. Data on the speed in miles per hour for a random sample of 30 cars traveling along a highway was collected. The mean speed was 63.3 miles per hour, and the standard deviation was 5.23. Now, those are both statistics, right? Because they come from my sample of 30 cars. So if you want to jot some things down, you can say x bar is equal to 63.3, and my sample standard deviation is equal to 5.23. So part A says find the 95% confidence interval for the mean speed of all cars traveling on the highway. So let's go ahead and take a look at that. I'm going to skip the details for now about verifying the conditions, but I am going to show you what to do in StatCrunch, and I have some screenshots here. So where you're going to go, first of all, to get to this, you're going to go to Stats and then T-Stats this time. So this is under your Stat menu. You're going to go to T-Stats. select one sample, and then with summary. And just like it was before when we did proportions, you're going to put in your information. You're going to put in your sample mean, you're going to put in your sample standard deviation, and your sample size. In this case, they told me they collected data on 30 cars, so N is 30. Then you're going to decide you want it to perform a 95% confidence interval and put in the level of 95%, and then this is what your output is going to look like. So what do we have here? We have a lower limit of about 61.35 and an upper limit of about 65.3. So my confidence interval for part A, let's go ahead and write that out. So our 95% confidence interval, and they didn't give me specifics, so I'm just going to round it. I'm going to say 61.3 to 65 looks like 3 as well. So I estimate that the mean speed for cars is between 61.3 miles per hour and 65.3 miles per hour. We're not doing proportions, we're not doing percentages. These are means, don't forget. So I have an actual number, there's no need to move decimals around or anything like that. So part B says to interpret this, so what can we say? Let's see, we can say we are 95% confident that the mean speed, so the mean speed of all cars on this road is between 61.3 miles per hour and 65.3 miles per hour. Now part C said, is it plausible that the mean speed of cars is 67 miles per hour? Well, what do you think? If my lower limit is 61.3 and my upper limit is 65.3, does 67 seem plausible? Hopefully you'd say no. So let's see, I'm short on room here, so I'm going to write it up here. So we'll say no, since 67 miles per hour is outside of the interval that we came up with. Okay? And that's all you're going to do. Let's try another one. A random sample of 35 college students was asked how many movies they had seen in the previous month. The sample mean was 4.14 movies with a standard deviation of 10.02. So construct a 90% confidence interval for the mean number of movies college students have seen per month. And so, again, we're going to go to StatCrunch. We're going to put in our mean, our sample standard deviation, sample mean, and our sample size of 35 students. We're going to select a 90% confidence interval and hit compute. And here's what your screenshot is going to look like. Okay, so this is the part that I'm interested in. So for part A, my 90% confidence interval is going to be from 3 to 7 movies per month. And I know it seems strange to say 1.3 movies because you can't see part of a movie. I guess you could, but remember it's an average, right? A mean is really a numerical average. So you can have numbers that are decimals, even if that doesn't fit with the actual data that you would be working with. So part B says, if we were to use data to construct a 95% confidence interval, would the interval be wider or narrow than a 90% interval? Well, it's the same rules we had earlier in the course back in chapter 7. So if we construct a 95% interval, it is going to be wider. It's going to include more standard errors in your margin of error, right? And so it's going to have to be a wider interval. So let's jot that down. So we'll say wider since we can just say since higher confidence means more, we'll say more standard errors are included in your interval. And then part C says, what would be the effect of taking a larger sample? Now, this is a really interesting question here. If we have a larger sample, what you want to think about is how does that impact your standard error? You have to go back to that every time. Let me go back to the formula here. This formula right here. If you have a larger sample, what does your N, if N is bigger, what does that do to your standard error? Because that's what's going to affect your interval, right? Your interval is affected by two things. Your interval is affected by your margin of error, which is made up of two things, T star and your standard error. So if T star stays the same, but your sample size goes up, that indicates that your standard error is going to go down, and that's important, and that's because of what's happening numerically in this formula. So let's write some things down. So if sample size increases, your standard error, just like it always has, your standard error decreases. So if your standard error decreases, that means you have a lower margin of error, and so that means you will have a smaller width for your interval. So larger sample sizes will create a smaller width, assuming everything else stays the same. All right, let's try this one. The IPEDS website, I'm not sure what that is, but the IPEDS website provides data on colleges and universities in the U.S. We took a random sample of 35 two-year colleges from this data and calculated 2 confidence intervals for the mean total enrollment of all two-year colleges in the U.S. Both intervals are based on the same sample. One of the intervals goes from 4948 to 16,170. The other goes from 3815 to 17303. IPEDS, there it is, Integrated Post-Secondary Education Data System. Which interval has the higher confidence level and why? So the easiest way to figure it out is to look at the widths, because remember, higher confidence means you've got a larger width or a longer width. So let's look at the widths. So for the first one, let's see, your width is going to be, let's do 16,170, take away 4948, and I'm getting a width of 11,222. For the second one, let's see, the width that I'm getting is 17,303, take away 3815, and the width I'm getting for that one is 13,488. So which one has a larger width? That would be the second interval that we were looking at. So the second interval will have a higher confidence simply because it's got a larger width. That's the easiest way to look at it. And then B says, what will be the effect of taking a larger sample? This is similar to the last question. What does a larger sample do? A larger sample reduces the standard error. The larger sample means your standard error is going to decrease, and that will reduce your width, smaller width, same thing. So you will have a smaller or narrower width. And why is that? Because the larger sample will reduce your standard error. Okay? How about this one? It says a study to test the life of iPad batteries reports that in a random sample of 30 iPads, the mean battery life was 9.7 hours, and the standard deviation was 1.2. The raw data were not made available to the public. So it says find and interpret a 90% confidence interval for the mean battery life of all iPads. Okay, so X bar, let's write some things down. So X bar for my sample was 9.7, and my standard deviation from my sample is 1.2, and the sample size was 30. Okay, so from StatCrunch, I don't have the details in front of me, but if I run the test in StatCrunch, I'm going to let you go ahead and do this on your own. Remember how to do this. You're going to the Stat menu. Let me look it up again. You're going to go to the Stat menu and then go to T-Stats, one sample, and then with summary. So if you do that, I'm going to get an output for my confidence interval, a 90% interval. Don't forget to put that in. I'm going to have 9.3 to 10.1. So let's just go ahead and interpret a statement for it. What can we say? We are 90% confident that the mean battery life for all iPads, so for all iPads, is somewhere between 9.3 and 10.1 hours. And that's what the confidence interval tells us. One more, a chain of pizza stores published data on the size of its pizzas to convince the public of their value. Using a random sample of 125 pizzas, so N is 125, the chain found that the mean diameter was 11.5 inches, so my sample mean is 11.5, and the standard deviation for my sample is 0.25. Find and interpret a 95% confidence interval for the mean size of all pizzas for the chain. So again, using StatCrunch, I'm going to get an interval that goes from, 11.46 and 11.54. So let's just write up the interpretation of that. We will say we are 95% confident that the mean pizza size for all pizzas for this chain, because that's our population is the chain, it's going to be between, because there's always a little fluctuation, but it's going to be between 11.46 inches, I think it was, and 11.54 inches.